part of this this discussion, where we're going to talk about circularity challenges and drivers. And my talk will sort of deal with the initial part and try to set a framework for where we are in terms of aluminium and circularity and recycling activities. And hopefully, for some reason, I cannot move forward. Now we come here. Yes, perfect. So the first part here is that we will talk about sustainability, and I will talk a little bit about the primary aluminium, a little bit on production and demands, and improvements and issues and usage growth. And when it comes to recycled material, we will take a look at what drives the recycled material. And there are also some efforts that are giving us a greener and greener activity. And in order to really learn something from this, I think that we need to find the apples of knowledge here in our green garden, and things that we should try to think about and prepare for the panel discussion is a little bit on how to handle the increased material mix, how electrification drives change and affects the material mix. And if you also think about what the foundation of this affects in component design and also consequences of recycling. Now, starting with sustainability, this is a very broad topic, and we can always have our own view what this is. But there is a framework developed by Broman and Robert for a strategic sustainable development, and it's in Journal Cleaner Production. Essentially, they divide it into two halves. One part is socio-economic sustainability, and the other part is ecological sustainability. And when we talk about sustainability, most of us are thinking about the ecological sustainability, which means that we should try to minimize the use and extraction of resources. We should not pollute our environment, and we should minimize the wear and tear in all our applications that we use. But it also so that when you look at sustainability, it affects health aspects. We should not use alloying elements, for instance, that might be ecotoxic. We need to have an empowered participation of the individual. We need to have personal development, and this webinar is definitely one part of that effort. And a fair and non-discriminatory society and meaning-making existence. But this means also that if we think about, in order to be able to access our capability, we need economic drives, we need economic success of the products that we actually use as well. So that is an enabler for these activities. Now, one thing, when you take a look at the role of in sustainability for the automotive industry, what we know from cars is that well, almost all the energy is consumed in the use phase. And to the right here, we have a life cycle analysis for a Volvo XC40, and then a number of Polestar cars. So in a petrol environment, this orange here is the carbon emission during the use phase, and the gray here is related to manufacturing. Now, when you go electrical, everybody says that there is a huge impact from the battery, and that actually in this case corresponds to about 50,000 kilometers of driving. But it's still so that there's a fair amount of carbon emissions coming from the use phase. Now, if we change our electricity mix and go completely green, what remains is essentially the carbon footprint from manufacturing. So if we're looking at the energy mix transition, that is only part of the problem that we need to deal with. And the thing which is probably more difficult to change is the materials and the way that we produce the materials, which still is binding a fair amount of carbon emissions into the use of our cars. So what comes what becomes very, very important is our material choices. That means that we need to have the right type. We need to have a good material source. And it also means that we need to choose the proper process. So this is a very strong driver to change how we do things and how we select our materials. If you take primary aluminium as one example, which is quite a strong source of carbon dioxide, we can see that in terms of production, we've been having a steady growth from the 1950s and but in around the change of the millennia, we had a rapid increase. And that is essentially because we have the growth in Asia, where the middle class is growing and the use of cars and such are growing significantly. We also have changes in the electronics industry, where we have increased demands on aluminium. So that is one thing that is changing in terms of the production. And in terms of demands, this cannot go on forever. So if we see here, this is about 2020, so we are about here somewhere. And it will continue to grow a little bit. What you can see also is that it's projected that Africa will start to use a little bit more, and India will come and start to grow, and the actual boom in China is going to recede. But as you can suspect, there will be a boom from India, for instance, afterwards, which actually will affect activities. Now, in Europe, we've been having a very clear vision on how to reduce carbon emissions with responsible production, innovative applications, and also socioeconomic contribution. And we are sort of in some kind of midterm review here, and we are driving on towards a more efficient situation. And that comes back to how we produce the material and also how the energy to the material is coming. So if you look at the global average, we are about, for aluminium, 18 kilograms of carbon dioxide equivalents per kilo. And in Europe, we're down to 7, and China is around 20 here. I should say that if you look at the energy per kilo of primary aluminium, we actually consume a little bit more energy in Europe than in China, because there's a lot of new large-scale installations in China. So this is driven by the electricity mix in China. If you look at the different sectors, we have here projections for various years. We see that transportation is projected to grow very, very strongly. We have also electrical applications that are growing very strongly as well. And you can see that construction and machinery is not neglectable either. But the automotive transition is primarily driven by the electrification, where maybe we have 120 kilos per car, and people are talking about 300 to 400 kilos of aluminium per car. And the electrical and electronics comes from large expansions of 5G stations, and also the fact that we use electric drives in more applications than in cars. And that means that in order to sustain this, we cannot solve this problem in growth just by primary aluminium, because that will not keep the carbon dioxide footprint down. We need to actually recycle materials in order to manage this. Now, if you look at what's driving the change, one thing is what you would call light mobility, which is cars, trucks, and lorries and buses, and also aircraft. And a large game changer has been what Tesla has been inventing, where you have the Model 3 and the Model Y, where the whole rear part of the car is being cast in a single piece. And this is actually, one of these pieces used to be several aluminium alloys and consisting of about 70 to 100 components. And that means that you save up maybe 70 tools, 70 procurement processes, and you get also a single material in this whole part, which means that it allows better recycling. The thing is, you need to change manufacturing quite dramatically, and you need to cast. So this is one large change. This requires large machines. And as a matter of fact, if you look at the electronics, it's also so that the 5G applications also are driving larger castings. So that means that the need for large machines are increasing, both from the telecom industry, maybe going from 1,500 tons to 3,000 ton machine. And when we're talking about this, it's 6,000 to 8,000 ton in locking forces and such. So that is also a part of the scenario change that we are looking at. Now, it's not the only area which is driving. So we have low energy consuming buildings. We have applications, building performance solutions for windows, curtains, and walls, ventilated facades, and things like that. That will also drive the use of aluminium. And this might be maybe more into the sheet and extrusion area than casting area. We have resource efficient packaging. One of the important capabilities of aluminium is that it's a very important oxygen diffusion barrier. And that means it's very often used in food packaging and such as well. And that means also that we need to see how to develop packaging and such as well. But that is also foil, so it's not that large a tonnage. But it all comes back to that we need to understand recycling and how to effectively use recycling and how to drive what is seen as an essential for a circular society here. Now, looking at two different scenarios from the European Aluminium Association, where we have a realistic scenario for primary production in Europe, and then we have, a slightly different scenario with this decreasing production for primary production in Europe. The thing which is different in these is essentially the mix of the primary aluminium. The recycled aluminium is still getting the same type of production independently on where the primary material is being produced. And it ends up at 2050, about 50% of the volume that is being produced. Now, we look at the benefits of recycling then. One thing is availability. And of course, 75% of all the aluminium produced is still in use. And we know that if you recycle the material, you sort of save 95% of the energy used in the primary production. And we have relatively good recycling rates. And I should say that recycling rates in Sweden are higher, but these are averages for Europe here. So that more than 90% of the material used in construction is being recycled, and 90% in the automotive industry, and in packaging, we have 60%. And when we look at that, of the scrap that we are producing in Europe, 10% is being exported here. And this is of course something that it's part of the international trade, but this also corresponds to energy investments and such. I will come back to that. When we look at recycling rates, we are #1 in Europe in recycling, followed by North America and then China. And Latin America and Middle East are not really up in terms of per capita, but this is also naturally related to the amount of usage per capita as well. So if you don't use that much aluminium, you will not recycle that much either. Now, looking at the scrap export, these are just numbers to illustrate that we used to be an importer of scrap, but we are now a net exporter of scrap in Europe. And that means that what we do is essentially invest in energy and then we export it. And the net export that we actually have corresponds to, if you compare that to some kind of energy usage, it corresponds to 20% of the energy usage in Denmark. So it's a fairly significant amount of energy that is being transported to other countries in terms of energy investment here. So by closing the loop locally, we reduce transport, and by closing the loops, maybe also within different material classes. We will hear more about that when Christina talks later, and she's more into the recirculation loops. But anyway, all this comes back to that we have a need to effectivize both the production of primary aluminium and also the recycling processes. And what is common for both of these is the energy source. And when you look at the green investments in terms of megawatts, you can see Norsk Hydro is a large investor in green energy, and that's also because they're an aluminium producer. And not far down the list, you also find Alcoa as a user or investor in green energy. What is also going on is, of course, a transition when it comes to the supply of primary aluminium, and there has been a rather large development in producing carbon-free primary aluminium, where the source of carbon comes from the use of the carbon anode, and there are now other types of anodes. And there are two leading efforts, or actually there are three leading efforts, I would say. One is Alcoa, that has, through Elysis, they're setting up a demonstration facility. The other one is Rusal in Krasnoyarsk that are developing this. I have not come as far as Elysis. And then there is also a Icelandic effort on this. So there are things changing here. I should say one of the issues with this is that you get impurities with change of electrodes. So they are also developing cleaning activities, also driven by Alcoa. So they have the Elysis and the Astraria processes. Now, that is roughly what I wanted to say, and then I would like to hand over to Christina. So please, Christina, the floor is yours.
Yes, thank you. So, just to see to get the slides up. Sorry, it will just take a moment for it to go up in presentation mode. So
I think we're seeing the wrong thing, Christina,
yes,
right now.
Yes. I am...
Now, yes,
no.
Perfect.
Now you can see it. Yes, excellent. So I will continue from where Anders left us, and the work presented here is effort together with Anders and Lucia at Jönköping and Andrea at the Lund University. So as Anders described before, is that we stand in for a huge challenge to be more circular and take care of our resources in a better way through better recycling. And if we look at how the state is today, about 8 to 9% of the global society today can be considered circular, which means that we have a huge effort in front of us in order to realize a sustainable society. So one of the absolutely key, strategies is, of course, to be better at recycling, to be able to, increase the circularity in our societies. When we talk about metals, we think of them as having a great sustainability advantage, as they are fairly easy to recycle in terms of that we can melt it down and we can reuse it. But this is in theory. As often when we use metal, we doesn't use them in the pure form. We use them in different type of alloys. And when we are mixing different alloys and so on, we get a lot of impurities and we get a lot of losses in terms of things that we cannot recycle in a good way. So we need to be better at recycling our metals in order to use the advantage of them to actually be a sustainable materials for a circular society. So this will just be a little bit, Anders showed you before, how we utilize resources are continuously increasing a lot, not only in aluminium, but in all type of resources. And this is one part of the challenge, that we need to be better to reuse the things we already have extracted. If you look at how well we are at having productivity and productivity increase, we can see that the labor productivity, energy productivity, and the greenhouse emissions productivity is steadily increasing. And we have, say, at least a fairly good exchange between countries, and overall a global increase in productivity. But when we look at material productivity, we can see here the blue line, that is actually not that well. I say we are not as good at utilizing the materials and utilize them in a productive way as we are with other resources. And some of the, talks about why this is that we have a tradition that if a country has reached a certain majority, a certain level of productivity when it comes to materials and so on, we have increased the technology, we tend to want to put the material production, outsource that material production, because of the very energy, we need a lot of energy, we need a lot of work in order to refine the materials. And we tend to only have the last step of the production in country where we have developed the technology to a good level and a good standard. It means that when we are pushing the costly and also some of the labor intensive activities from the high cost countries, we are also not making all the technology available for the production of our materials. So that is some of the reason why we think that the material productivity is not as good developed as other productivities in the world. And you can find this more in the Global Resources Outlook from the UN. And this one is in 2019. There may be a newer version of this outlook. When we talk about metals, it's something that is really important for our society, but I also think it's good to have in mind a little about the quantities. So aluminium is the second most used metals that we have. And if you compare it with iron, of course, there's a huge difference. But on the other side, aluminium is also a lot lighter. So this is, all the materials here are in tons. So that means that the volume, of course, is larger than what this picture shows. But we also see that we have a lot of other materials that are precious or very important for our technologies and so on, but we doesn't use or extract in that high volume, which means it's even more important that we take care of these metals. So when we are producing alloys and so on, we not only need to consider the primary alloys, the primary source, in this case, aluminium, but also what do we actually add to that alloy and how do we make sure that these precious metals are really taken care of and that they not go into impurities, but actually providing something to the recycled material. As Anders described before, the cast product is at the moment the major part of the aluminium products. And here's two forecasts of how it would look like, depending on if you have a low or high forecast. And here we can see that the cast aluminium is still absolutely the major part when it comes to the products. And then we have some other extruded and forged and rolled products and so on. But this also means that when we are changing from, usual combustion engines to electrical engines in our vehicles, we, doesn't need as much cast materials. So approximately about 40 to 50% of the parts in a combustion vehicle of aluminium or cast aluminium need to be transformed into wrought aluminium, which means that we cannot, use cast products as the end of life products anymore. We need to think about how could we recycle products in order for them to be wrought aluminium and not cast aluminium, which is in one way a big challenge, because we can accept a lot more impurities in cast aluminium compared to wrought aluminium. If we look at the losses that we have in aluminium, is that when we are producing a new cast aluminium product, even if that product can accept a lot more impurities and so on, we need to add about 20% of virgin aluminium. And we also, in average, we lose a lot of aluminium when we are recycling it, and it could be up to 45% of losses. And most of the losses could be related to when we are remelting the material. And it could be good to know that even if a metal in itself, I say, could be remelted and so on, we have materials that are oxidizing and so on when we are remelting. And so we doesn't have an infinite number of times that we can remelt an aluminium before everything has gone to losses that we need to recover again in some way. The demand of wrought aluminium will increase the need for virgin aluminium. And if we need about 20% of virgin aluminium when we are producing a new cast aluminium product, we need a lot more when we want to recycle wrought aluminium with today's way of recycling. Today, we reuse about 35% of the aluminium used in Europe is from recycling. And this is estimated to increase, just as Anders showed you before, to 2015. And the way that we're doing it when we recycle today is that we often are downcycling or downgrading materials. So it's not often that we can recycle one product and use it for the same purposes again. For one example, we can take the aluminium cans, for example, that we think is a really good, I say, closed loop recycling. But actually, we have two different types of materials. We have one material for the lid, and we have one material for the bulk materials on that can. And when we're recycling it, we can just use everything for the bulk or for the body again. And we need to add new materials for the lid. So one way, that is not a closed loop recycling, because we need to add new materials to make sure that we are meeting all the requirements for that product. And it's the same for many other materials also, that we need to add new materials. And in that way, we doesn't have closed loops, and we downgrade when we are recycling today. And what is also important to know is that cast products have a relatively low value or material value compared to wrought aluminium. So you also lose a lot of value when we are recycling. And I think we should not forget that Europe aluminium production today has a lot lower carbon dioxide emissions than the global average. It makes it important that we also think about that we should not only produce aluminium, we should also be a great aluminium recycler here in Europe to make sure that we are utilizing the good mixture of electricity here to reduce the footprint of aluminium products. There are different forecasters and so on, but some forecasters are estimated that we will need about thrice as much aluminium in 2050 than today. But there are also other forecasters that predict lower levels. And as Anders shows, there are also a prediction that we should use about 50% of the consumption should be from recycled materials. So that means that we need to do a lot of improvements in our current chains. And just as Anders also told you, we have about 1 million tons of scrap aluminium that we are exporting today instead of taking care of it where we are scrapping it. And that means that we not only, I say, missed opportunity to lessen the carbon footprint of recycling that scrap, we also miss a lot of money in selling that scrap instead of taking care of it. So the backside of recurrent aluminium recycling, I already mentioned some of them, but we can see that impurities such as iron content is steadily increasing. And that makes it, and this, I say, alloying element makes it quite hard to purify from the alloys. We also see that we have a lot of remelting losses that are accumulating impurities. Such as copper, ferrous materials, and oxides are limiting the number of times that we can recycle aluminium products. And also that we increase the complexity of our product. We are continuously designing new materials for new end uses. And that means that we, instead of thinking about how we should recycle it, are focusing on how to make the best product. And that in turn makes it even harder, because that means we add more variety and more alloying elements that could end up being impurities in the recycling. When we look at aluminium classifications, we have several different classifications, and they of course have different type of alloying elements or main alloying elements. We have the first class, the 1XX series, which are more or less pure aluminium. Then we have the alloys with the copper as the main alloying ingredients. We have alloys which have a manganese, alloys for silicon, and then magnesium and silicon and magnesium and zinc. So we have quite a good structure on how we define different types of aluminium alloys and how we classify them. And there's also classification for both wrought and for cast aluminium. However, when we are looking at the European standard for recycled materials, we are not, I say, sorting scrap that much into what type of alloying elements they have. We are sorting them based on what they have been used for. And of course, there are connections to how we use materials and what type of alloying elements we want to have. But there's really no good cohesive way of comparing the standards of the aluminium alloys with how we are recycling them into, I say, a new alloys. And that in one thing be a hard thing to make sure that we actually are making a secondary good materials for recycling. Of course, it's really good that we can sort things that is easy to sort, but we think that we need to improve the way of how we are refining the ways of recycling materials even better in the future. If we look at the different say major alloying elements, we have copper, for example, that we have for strengthening the alloy and also to make it better for heat treatment. As I said before, it's the main alloy for the second 2000 series. And it's not uncommon that we also have it together with manganese and zinc. And also copper could have a negative effect on the weldability. So there are both positive and negative sides of the copper. Manganese is also another important alloying element, and it's improved the dispersion hardening and provides good corrosion resistance. We have silicon that are, I say, usually used when we are making cast and forging products. It's especially good when we want to produce thin walls products. And it could be, how say, used together with magnesium and copper and nickel to, how say, make sure that we also have, I say, a solid system that have a precipitation hardening. Magnesium and zinc are other alloying elements, and magnesium is solution strengthening and heat treatment, and zinc together with magnesium also has a increased the strength by precipitation hardening. There are of course other alloys also. We have, for example, titanium and boron that is used for grain refinement. There are other, I say, elements that we want to add, also to make sure that we, make sure that we doesn't have too bad influence from silicon. And instead of having it has a brittle flake-like structures, we get more fibrous structures and so on. So, but when it comes to impurities, of course, all the alloying elements can become impurities if they are in the wrong applications. But we have phosphorus and iron as one of the, main impurities that we really need to take care of. Phosphorus, because it's acts as a nuclear agent for silicon crystals, in that way could make the material quite brittle. And then we also have iron that we want to use for some applications, but it also reduces the ductility and tensile strength. So iron is something that we may want in some of the cast applications, but it's usually nothing we want in the wrought aluminium. So this is the two main alloys impurities that we really need to get rid of when we are recycling aluminium. So there are different ways of how we can go about and looking at recycling. The first one is closed loop recycling. The second is, and could also support the closed loop recycling, is how we sort and prepare the solid waste before we are going for the melting. We can also purify the melts, or we can add reagents to neutralize impurities. We could also look at how that we can add either pure aluminium or alloying elements in order to make sure that we meet the specification of the materials, or we can decide that it's okay that we can accept other materials or accept downgraded materials by changing our specification even more. So not only look at the absolute the best solution for the material, but see which of the different materials could we actually accept. So when we look at that closed loop recycling, one of the benefits is that we could reduce the energy consumption in total, and also that we could increase the metal recovery rate. And of course, in practice, it's really difficult to reach 100% of recovery because we will always have some losses related to the recycling. What we can see is that a lot of the impurities that arise could also come from tools, coatings, when we have processed the materials. And that means that even if we're really good at treating and having a closed loop, we will have impurities from the processes. And also that we will have some oxides that are, occurring when we do the recycling. And what is also important to remember is that even if we have a closed loop recycling, we will even minor impurities, if we are having several cycles, they will accumulate during the process and so on. So we will need to have some treatment in a closed loop recycling to make sure that we are not accumulating too much impurities. One way of reaching this could, of course, be that we say that, okay, we need to define a lot more what we are using each of the different type of alloys for. As we saw before, we had the different, 1 and 2 and 3 and 4 and 6,000 series of aluminium alloys, and we had a different way of handling scrap from different applications. So if we can connect even more that, okay, 3,000 series should be heat exchanger, turbines, and chemical piping. And we know that, okay, all chemical piping is from the 3000 series. We could have a lot better way of saying, okay, then we know that when we get a chemical piping, we should put the pile for 3000 alloys, and that should become a 3000 alloy again. And so forth we can do with other things. So we are not only sorting by the application, but we already defined that for this application, we are only using this type of alloys. So that could be one way of how we could control and make sure that we have a closer way of reaching closed loop recycling. And then, of course, it's not, we cannot only look at, a way of controlling iron and copper with, dilution. So we need also to think about how could we, how could we refine the materials even in the closed loop without adding new materials. So the next step, of course, and to realize closed loop recycling is to have better sorting. If we look at the picture here, when we are, for example, scrapping a car or recycling a car, this is not how it looks like. It's too costly and too expensive to, disassemble everything for recycling. So what we do today is that we shred it into small pieces, and we try to, separate each of these different small pieces. And that's, make it have a lot of different materials in the waste stream that we need to sort. And when we are separating this, we can use magnets, we can use conductivity. It could be color sorting by hand or by having some different visual techniques. We could, for example, also take in consideration what density it has, use X-ray and 3D shapes and so on, to try to figure out what is the material that we are seeing and what pile should be sorted to. Unfortunately, these methods are not really well functioning if we want to separate different materials and make sure that we only get a certain materials in a pile. For example, there's been done studies for cars, and there they could see that joints, for example, as screws and bolts and rivets and so on, could contribute up to 69% of the total iron impurities in the aluminium scraps, which means that we will be using iron-based screws on aluminium plates. And I can see the same things for the bike I have at home. I have bought an aluminium bike, but even as it's an aluminium frame, they still use iron-based screws. So we need to start thinking more and more about how do we mix materials? Could we mix, could we not mix materials and make sure that the joints are made of only one type of materials? We are not, because if we're shredding, we cannot separate the joints from the main materials. The only way to achieve that is to shred it into even smaller pieces, and even then we have a high risk of still having a lot of impurities due to mix of materials. So manufacturers should be restrictive with the materials they use in mechanical joints. And as I said before, recyclers, if we still mix them, recyclers need to shred materials into even smaller pieces and use really strong magnets if they want to separate this. And part of the problem here also is that a lot of ferrous materials are not magnetical. So we still need to have other ways of sorting. So, and what we also should remember is it's not only that we should sort scrap based on, on what it is, we should also sort it on what it should become. And that means that we need to sort it as close as possible to the secondary material that we are going to produce. And there's been done some technical studies for materials with iron, copper, silicon, and manganese content. We can see that it's possible to do it, but we still need to refine it and make it more costly. What's also important is that we should decoat material before it melts. So here, for example, is a decoating furnace that could be used, because if we are using visual systems or other things, if we have a coating on the materials, it's really hard to see what is this, what type of alloy are we looking at, and so on. So the coating is something that we need to do, and also because we doesn't want to have the coating in the mix. Another way is that we can use melt purification, and it's generally hard to purify aluminium, and some of the reason this is that aluminium has quite a low melting point. So most of the alloying elements have a higher melting point than the aluminium, and also that aluminium have a higher affinity to oxygen, which also could make this hard. There are, of course, some major exceptions for this, and the zinc and magnesium. And then also in some alloys, we could have a small amount of tin and lead that also have, are a little bit easier to take away from the melt. Magnesium and kalium and beryllium can be removed by oxidation. Zinc, cadmium, and mercury could be removed by evaporation, and lithium could be removed by distillations. The other elements that are remaining in the melt are quite difficult to remove. And that's why it's really hard to reach a high purity without a lot of costs. There are several methods that we could use. Gravity separation, filtration, and centrifugal separations. This one we can use, for example, for iron, as iron is a lot heavier than aluminium. So this is one thing we could, if we're keeping the temperature at 650 to 600, 650, and so on, and use these three techniques, it is possible to reduce the iron content. We could also use electromagnetic separation for iron. There are also some other, ways of doing this. We could, for example, add mangan, chromium, and strontium to increase sludge formation, and in that way, take away the silicon and iron content. Electrolysis is suitable if we want to refine it, but it also comes with a very high cost. So that's usually why it's not that often used. We also have slag and rust recovery, and one of the things that are removed by this type of process is rare earth metals. And there has been some tests for a multi-stage electronic metallurgical methods that could achieve up to 97%. So it's a good potential. And there's also some indication that this could be scalable to a low cost. And that this is recovering more elements than the current methods used today. So it's still not a method that is used for the recycling industry, but it may be something that could be used for the future. There's also the possibility to add reagents to neutralize the impurities. And of course, the disadvantage is that the impurities will still be present, even if we add these reagents. And they will also accumulate in contact. The problem with these reagents are that many of them are expensive. If, for example, look at cobalt, it's both a CRM, but it's also a conflict mineral. So most of the reagents here are not sustainable to add and even worse if we add it just to make it, say, neutralize impurities, not because they have a great addition to the aluminium in itself. We could also, as I said before, dilute high purity aluminium with alloying elements. And that could be both virgin materials and high quality recycled aluminium can be used. And this, of course, will increase when we are, leaving the combustion engine and going into electrical vehicles. And there's, of course, a high risk that we will need even more virgin materials in the future for this type of ways of making sure that we have higher purity in aluminium. Another alternative is that we could change the material specifications, that we accept a more difference in materials. But this could also mean that if we change the specifications, then it's not about only changing them, maybe that we should have a higher flexibility in what of the different type of alloying elements that we can accept. So it doesn't drive a demand for more alloys if we're not is needed in one, just because that the specification is telling us this. And of course, there's the problem is, of course, that we have some institutional barriers that restrict us to use of recycled materials, and that could be for safety reasons and so on. So it's not a simple thing to do. So if we look at the outlook, we need to start with the losses. We have some different type of losses that we need to take care of. We have the collection losses. That is the thing that we need to be better at, making sure that actually the end of use aluminium go into recycling. We have material losses, we have quality losses, and we have dilutions losses. And the quality losses and the dilution losses are occurring when we are melting down the materials for recycling. Oh, I see. So we have volume also, and that is always really important that we have when we're recycling. If we want to reach a closed loop recycling, we need to have a high volume, because otherwise we will not be able to have an efficient flow and taking care of the new the material without adding new materials. So we need to make sure that we have a minimum of volume in the loop. There are some future, or they already exist as sorting techniques, but could be used even better in recycling. And that could be X-ray fluorescence. It could be, as example here, laser-induced breakdown spectroscopy, LIBS. And there can also be other techniques that we can use at better seeing the accuracy of the content of our recycled material. I see I'm closing the end time, so just some summaries. We need better techniques for shredding and sorting. We need to go for more closed loop recycling, and that is both for primary and secondary materials. We should also look at the scrap, and it should be analyzed based on its alloying content and not only for what it's come from and what has been used for. And we also need to look at future performance requirements to make sure that we, in the end, we doesn't only need to look at the cost now, we also need to look at the cost on a longer perspective. We could also use the composition of available material to gain the correct material characteristics. So that we should, we should try to either recycling as close as possible to the alloying alloys that it was before, that is after recycling, but also that we could use the alloys to make sure that we receive the correct new alloy. Instead of adding new materials, we add the correct alloys instead. And we should also make sure that we can use the byproducts, and that we can utilize the byproducts that we get. And what we should remember is that when we're recycling aluminium, the objective is not to produce a pure aluminium. It's about making an alloy that fits to the new application. Just a recap, aluminium, as Anders showed, are used for many different applications, which means that we have a really big variety of aluminium alloys, but also how it has been used and how it could have been contaminated, either during use or when we are producing the alloy. So that makes it even more important that we are thinking about recycling. We need to be better at recovering wrought aluminium and upgrading scrap. And that means that we will need a better alignment between existing scrap standards and the material specification from manufacturers. We maybe need to accept more general specification, and also that we need to develop the purification techniques for removal of alloying elements. Effective sorting should not only be from primarily based, it's not only based on the material price. And as I said before, the volume is really important. So, so effective sorting can also be driven by that we need a high material concentration, or that we have it's easy to separate. So we should not only think that effective sorting is driven by the raw material price, but also on how easy we make this sorting. And as a last thing, product design have an important role to achieve a material recycling or an effective material recycling. And we need to think about how we could minimize the contamination from different processes and as when we are shredding and melting and so on. So finding different applications to absorb the end of life cast aluminium is one thing, and also limit future downgrading. So
thank you very much, Christina, for a very nice and very interesting presentation. And of course, also thanks to Anders.